So we introduced this unit talking about rates of change. We talked about the average rate of change, which is important to note that it is the slope of the secant line, whereas the instantaneous rate of change is the slope of the tangent line at that particular point. So we now know that the instantaneous rate of change is the derivative at a particular point, the initial point. And we know the limit definitions that we've talked about already so far this unit. So now we're going to look at how to apply them in some sort of word problems. Here's an example we're going to start with. Find the instantaneous rate of change for the area of a circle when the radius 3, and also the instantaneous rate of change when the area of the circle is 4. A couple important things that you need to know off the bat is your area formula for a circle, pi r squared. So this is our y value, that's our x value. If we were to look at this in terms of an actual function, we can see that it is, your area is going to be here, your r is going to be here. At 0, your area is going to be 0, and we're going to see that it's going to grow something like this. So we're looking at this type of graph. Now, because we want instantaneous rate, we're looking for the slope at the point of tangency, when radius is 3 versus when the radius is 4. So what we need to then find is our derivative. Now, we're talking in different variables here. We're derivative of our area with respect to the radius. So that's what we're trying to find here. Now we have our formula here. Now we can also basically say it's the same thing if we're taking the derivative with respect to r of pi r squared. Now, the variable that we're taking it with is r. Pi is a constant, so keep that in mind. So now we can take the derivative with what we know in terms of our power rules. So 2 times pi times our radius to the degree of 2 minus 1, right? We're using our power rule. So it's 2 pi r, which happens to be circumference as well. Now they're asking for the rate of change when the radius is 3 and when the radius is 4. So specifically, we're actually looking at finding the dA dr when r is equal to 3, which means that we use this formula here when we plug in 3, which means that we have 2 times 3 pi, so we have 6 pi. We also want to find it, our dA dr, when our radius is equal to 4. So 2 times 4 is 8, so 8 pi. If we were to look at our graphs, and we have a point here for 3 and a point here for 4, we're basically looking at the slope at 3 versus the slope at 4. So now we're going to look at another question involving temperatures. So this example says that the temperature of an object at time t, where temperature is in degrees Celsius and our time is in minutes, is given by this equation for any value of t that's between 0 and 20 minutes. It's asking for what rate is the object cooling when t is equal to 8 versus when t is equal to 12. So again, we have to actually think about how you want to set this up in terms of your equations. So the rate of change that we're looking for is the rate of change of our temperature with respect to time. So big T versus little t. Another way of saying this again is that we're taking the derivative with respect to time for this actual function, which is defined to be this polynomial, which again is a quadratic, so we're looking at how it changes for when time is equal to 8 and when time is equal to 12. We're looking for the points of tangency. So we know how to take the derivative of this with respect to our power rules. So 2 times 3 over 8, subtract 1, 2 minus 1, right? Minus your 15, t, 1 minus 1, and then the constant becomes 0, right? So that works out to be, if we cross this out, 3 over 4 t minus 15. Remember, t to the 0 becomes the value of 1, so 15 times 1. So now I have this dt of d little t, and we need to actually evaluate these for 2 different values. We want to evaluate it for when t is equal to 8, and we want to evaluate it when t is equal to 12. So we will take this one here and plug in 8 wherever we see a t, and we'll take this one here and plug in a 12 wherever we see a t. So 3 over 4 times by 8 minus 15, which crosses out 6 minus that, so it'll be negative 9. In this case here, 3 over 4, plug in 12, minus 15, again crosses out, so 9 minus 15, so you're looking at negative 6. Now in this particular example, we also have to consider our units. Temperature is in degrees per Celsius, or degrees Celsius, and time is in minutes. So this would be negative 9 degrees Celsius per minute, degrees Celsius per minute. Also visually, if we were actually to graph this graph between our x values or t values, because little t would be here, temperature would be here, this would be in degrees Celsius, this would be in minutes. We are only up to 0 to 20, and in particular we're looking at 8 and 12. The graph itself has a y-intercept up here at 180, and it's going to actually drop something like so. Something like that. It's actually a parabola. If we actually spread it further along, we could actually see a little more detail, but we're only interested in from 0 to 20 because that's what the equation specified for us. So here at 8, we have a tangency here with a slope of negative 9, which looks right, and as we get here towards 12, we're getting flatter at negative 6. Still a negative slope, but this one is obviously a larger negative 9, more negative value for the slope.